Hi everyone, welcome to my presentation. Today I'm going to talk about my final project for Compeng 395 Scientific Machine Learning. So my project is about reproducing a paper called Ensemble-SINDy, which is a really cool method for discovering governing equations from noisy data, and it also gives you uncertainty quantification, meaning it tells you how confident you should be about the results. The original paper was published in 2022 in Proceedings of the Royal Society A, and all my code is up on GitHub, so feel free to check it out. Alright, so here's a quick overview of what I'll be covering today. First, I'll give you some background on the original SINDy method and explain why we need something better. Then I'll walk you through the Ensemble-SINDy approach. After that, I'll show you my experimental results on two systems, the Lorenz chaotic attractor and a real-world dataset, the Lynx-Hare predator-prey data. And finally, I'll wrap up with some discussion about the key findings and some interesting things I discovered along the way. Okay, so let me start with some background. SINDy stands for Sparse Identification of Nonlinear Dynamics, and it was proposed by Brunton and colleagues back in 2016. The basic idea is actually pretty elegant. Say you have time series measurements of some dynamical system, you compute the time derivatives numerically, and then you build a library of candidate functions. In my experiments, this library includes all polynomial terms up to degree 2. So for a system with variables x, y, z, the library would have constants, the variables themselves, their squares, and all the cross products like xi, es, es. Then you solve a sparse regression problem. You're trying to figure out which combination of these candidate terms best explains the observed derivatives, but with a sparsity constraint, because most physical laws only involve a few terms. The algorithm used is called STELSC, sequential thresholded least squares. It basically does ordinary least squares, then sets any small coefficients to 0, and repeats until convergence. Now, SINDy works beautifully on clean data, no question about that, but it has two significant limitations. First, it's very sensitive to noise. Even a moderate amount of measurement noise can cause the algorithm to pick wrong terms or miss real ones. And second, maybe more importantly for scientific applications, SINDy gives you no uncertainty quantification. You get one set of coefficients, no error bars, no confidence intervals, and in real science, we really need to know how reliable our results are. Okay, so this is where Ensemble-SINDy comes in. It was proposed by Fasel, Cutts, and the Bruntons in 2022, and the idea is conceptually very simple but really powerful. Instead of running SINDy just once on all your data, you run it many times on different random subsets. Specifically, you create 100 bootstrap replicas by randomly subsampling both the rows and columns of your library matrix. Each bootstrap gives you a slightly different model. Now, from these 100 models, you can extract three really useful things. The first one is inclusion probability. For each candidate term, you count what fraction of the 100 models include that term. So if a term appears in 95 out of 100 models, you can be pretty confident it's real. If it only shows up in like 10 out of 100, it's probably just fitting noise. The second output is coefficient distributions. Instead of a single value, you get 100 values for each coefficient, which gives you natural error bars and confidence intervals. And the third output is a consensus model, which is just the median of the coefficients for terms with inclusion probability above 0.5. Now for my reproduction, I used PySINDy version 2.1, the Python implementation. The original paper used MATLAB, and as we'll see, this difference actually matters quite a bit. Alright, let me now get into my first set of experiments. I used the Lorenz system, which is the classic chaotic attractor. The equations are shown here on the slide. I use the standard parameters, sigma equals 10, rho equals 28, and beta equals 8/3. For the training data, I generated 5,000 points with a time step of 0.001 seconds. I tested noise levels from 0 all the way up to 30% of the signal standard deviation, and to make sure my results are statistically reliable, I repeated every experiment 50 times with different random noise. On the right side, you can see what the data looks like, clean on the left, noisy in the middle, and the time series comparison on the right. Okay, so here are the main results for noise robustness. The table on the left shows coefficient error and success rate for both SINDy and eSINDy. And success rate here means exact recovery of the correct model structure, meaning exactly the right terms, no extra, no missing. On clean data, both methods work perfectly, 100% success rate, essentially zero error, which is a nice sanity check. But as soon as we add noise, things get really interesting. At just 1% noise, standard SINDy still recovers the correct model 36% of the time, but eSINDy drops all the way to 0%. At 2% noise, SINDy is at 4%, eSINDy still 0, and at 5% and above, both are at 0. Now this is actually really surprising, and it contradicts the original paper, which showed eSINDy should do better. I'll explain why this happens in a moment, but if you look at the coefficient error plot on the right, you'll notice the actual errors are very similar between the two methods. So the issue is specifically about exact model recovery, not about how accurate the coefficients are. Okay, now, this is the most important slide in my entire presentation, so I want everyone to pay close attention here. Even though the success rate is 0%, look at what happens with the inclusion probabilities. This figure shows results at 10% noise, which is quite a lot of noise. The left heat map shows the inclusion probability for every candidate term in the library. The green boxes highlight the terms that are truly active in the Lorenz equations. Let me walk you through each equation. For dx dt, the true terms are x and y. Both show inclusion probability of 0.99 to 1.0, meaning they appeared in basically every single one of the 100 bootstrap models. For dy dt, the true terms are x, y, and s, and all three are above 0.98. For dgs dt, the true terms are z and xi. Z has 0.97 and xi has 0.92. So every single true active term has inclusion probability above 0.9, even at 10% noise. This is really remarkable. It means eSINDy knows exactly which terms should be in the model. The reason it fails the success rate is just that the consensus model also keeps some extra small spurious terms, but for identifying the correct model structure, it works perfectly, and this is really the core contribution of the eSINDy paper, and our reproduction completely validates it. Next, let's look at uncertainty quantification. This slide shows the coefficient distributions from the 100 ensemble models at 10% noise. The top row has violin plots, bottom row has box plots. The red stars mark the true values, and what you can see is that in every single case, the true value falls within the distribution. The spreads are wide, especially for bigger coefficients, but the truth is always captured. This is meaningful UQ that standard SINDy simply cannot give you. With regular SINDy, you just get one number. With eSINDy, you get the whole distribution. And here's a quick look at trajectory prediction. I integrated the discovered model forward in time and compared it to the true Lorenz trajectory. You can see it tracks pretty well for about 1.5 Lyapunov times, then it diverges. But that's completely expected for a chaotic system where even tiny coefficient errors grow exponentially. Okay, moving on to the data length study. These heat maps show how noise level and data length together affect performance, and the pattern is very clear. You need both low noise and enough data at the same time for reliable recovery. At 0 noise, even 200 points work fine, but at 1% noise, you need thousands of points, and at 5% noise or above, even 5,000 points is not enough for exact model recovery. Alright, now let me show you the real-world application. I applied eSINDy to the classic Lynx-Hare predator-prey dataset. This is historical fur trading data from the Hudson Bay Company in Canada from 1900 to 1920. It records the annual number of lynx and hare pelts, which is basically a proxy for their population sizes. We only have 21 data points, one per year, so this is quite challenging. You can see the predator-prey oscillation pattern clearly in the left panel. eSINDy discovered the following equations. For hare, dHdt equals about 12.7 minus 0.67 times L. This means hares grow naturally but decrease when there are more lynx, which makes total biological sense. For lynx, dLdt equals about negative 17.2 plus 0.54 times H minus 0.05 times L. So lynx decline without hares but grow when hares are available. Now you might notice the classic Lotka-Volterra model should have Anhel interaction term, but it's missing here. That's because 21 data points just isn't enough to resolve that nonlinear cross term. Here are 3 more plots from the Lynx-Hare experiment. Top left shows the inclusion probability heat map, bottom left shows the coefficient distributions, and on the right is the reconstruction with 50 and 95% confidence intervals. You can see the model captures the oscillatory dynamics pretty well, and the confidence bands are wider where there's more uncertainty. This really shows that eSINDy provides useful uncertainty quantification even with very limited real-world data. Okay, so let me now address the elephant in the room. Why does eSINDy get 0% success rate in our experiments? After careful investigation, I found the root cause. It's an implementation difference between PySINDy and the original MATLAB code. PySINDy version 2.1 applies the stealth algorithm with a fixed sparsity threshold across all 100 bootstrap samples. But the original MATLAB code uses adaptive thresholding that adjusts for each bootstrap individually. What happens is PySINDy's version tends to keep tiny spurious coefficients in the final median model, and those extra terms cause it to fail the exact match criterion. But, and this is the crucial point, the inclusion probabilities are completely unaffected by this. All true terms still consistently show probability above 0.9. So the core contribution of eSINDy, which is robust structure identification through inclusion probabilities, is fully validated. The discrepancy is only in the final thresholding step, not in the methodology itself. Alright, let me wrap up with 5 key takeaways. First, inclusion probabilities successfully identify the true model structure even at 10 to 20% noise. This is the most important result. Second, eSINDy provides meaningful uncertainty quantification through coefficient distributions. Third, our data length study shows that reliable recovery requires both low noise and sufficient data at the same time. Fourth, on the real-world Lynx-Hare dataset, eSINDy discovers interpretable predator-prey dynamics with meaningful uncertainty bounds from just 21 data points. And fifth, the success rate discrepancy we observed is a PySINDy implementation issue, not a fundamental problem with eSINDy. That's everything. All my code, figures, and the report are on the GitHub repository. Thank you so much for listening, and I hope you found this interesting.